Hi, welcome to our 2024 OCP Storage Tech Talk. I want to welcome today. I'm Ross Denfort from Meta. I am the storage project co-lead along with Lee Pruitt and Mike Allison. And welcome. I also want to thank our sponsors, FADU, Micron, Samsung, SandBlaze, ScaleFlux, SiliconMotion, Telemetry, LaCroix, Western Digital. I want to thank you all for sponsoring today's event. And how about if we get started? Let's start off with celebrating our wins here. In 2022, we had a whole bunch of things that got contributed, all big wins. I do want to note that's when we first started our first OCP Storage Tech Talk. And then in 2023, we had a bunch of contributions. We had the NVMe HDD, the SASA device spec, the data center NVMe SSD spec version 2.5, telemetry scripts, and we did our second OCP Tech Talk. And that brings us to 2024. In 2024, we have a whole bunch of things coming. We have a SASA device spec, past the Rev 1.0 coming. We have from HP, Dell, Meta, Microsoft. We have the data center NVMe SSD spec version 2.6 from Dell, Google, HPE, Meta, Microsoft. That is also coming. There's an EDSF SSD reference design coming from ScaleFlux. And OCP Marketplace has picked up a lot of steam. There are 8 SSDs. There are multiple testing services. And we also have our third OCP Storage Tech Talk today. Lots of great progress. Now, let me bring you to the agenda. That being said, we did have some conflicts. So we are going to move the Hyperscale fleet learnings to be after FTP in this schedule. But this is our rough agenda. So we'll go through live migration, FTP, Hyperscale fleet learnings, community update, device spec, storage resiliency, lock, and then we'll close things out for today. So with that, we have a lot of exciting things coming. On the logistics side, I encourage everybody to be present for this great content and engage. If you have questions, type your questions into the question answer box. That's not the chat box. So if you go under the more with the 3 buttons menu, you'll see a question answer box. Put your questions in there. The questions will be answered based on time, availability, and we'll follow up with unanswered questions after the event. Also, the recording will be available after the event. And with that, let me hand it off to Mike for live migration.
Hello, everybody. Let me get my screen sharing here. Can everybody see this?
Yes.
Okay. I'm Mike Allison. I work for Samsung, where I'm a senior director working in our NAND product planning team, where I focus on standards. And here I am today to talk about NVM Express's host managed live migration technology that is being developed as we speak. To begin with, before I actually get into what NVM Express is doing, I want to talk about what are the use cases driving this. One of the use cases is just about balancing workloads in the system so you can deal with new workloads, for example. So let's just say, for example, you have a data center with a couple of servers in there. In these diagrams, you're going to see that I'm going to have a hypervisor that is connected to a controller that's used to manage the virtual machines that are in the servers. Each virtual machine, for this example, is connected to one controller, and then it has allocated storage space within the NVM subsystem. And I'm showing locally attached. You can think of the NVM subsystem as an SSD, but since I'm talking NVMe, we always describe it as an NVM subsystem. So we have this scenario here in your data center, and a customer calls up and says, hey, I have a new workload. And since this is storage, we'll talk about the storage associated with that new workload. And if you look at the new capacity requested, And as you look at your servers within the data center, you see that the new storage does not fit. So what live migration is going to provide is the ability to take a virtual machine, the attached controller, and the namespaces attached to that controller, and allow them to migrate it from one server to the next. And then that way it frees up resources such that this new capacity will be able to fit, and then you can go ahead and take that new workload and put it in a server and meet your customer request. Another use case that we always talk about is hardware maintenance. So here again, here's another example of a couple of servers with the resources allocated as I have diagrammed here. And you need to do maintenance on the server on the left, and it's running virtual machines. So just like with the load balancing for the new workload, you can take a controller and migrate it off to another server to help to start reducing the resources that you want to do for the maintenance. But for live migration in NVM Express, we want to be scalable. So we're also allowing multiple migrations to happen in parallel. They don't have to be sequential, and such that the host can then move them all off to multiple servers, or here, in this case, I showed one, but wherever the destination server is, you can handle it in multiple locations. So after we moved all the virtual machines, there's no resources being utilized. The server can be taken down, maintenance could be performed, server can actually be brought back online, and then new workloads or existing workloads can then be migrated in and then continue with your processing and balancing within there. So let's get into what is live migration that we're doing in NVM Express. So really what I want to talk about is host manage is really important word when we look at what we're doing for the live migration. The host is doing a bulk of the work. What NVM Express is doing is providing services to the host. One of the services is, hey, how do I get the NVM state from the source server or the controller that we're migrating to another subsystem? And then it's up to the host to get that state. It's also up to the host to actually migrate the data from one server to the next. That's outside of the scope of NVM Express. And then once the host actually moves it over to the other server, then we need services to put that state in and to reserve it. So we're going to talk about what these services are provided, and I'm going to start with the NVM source subsystem first. Excuse me. So the first thing we want to do is read allocated logical blocks. So part of the migration is when you're migrating live, you have to take a static view of the state that you're migrating, copy that over, be able to log various things while the VM is still running of those changes of the static view. Then at the end, pause everything, migrate the final change state over, and then resume. And I'm not going to get into all those operations that I showed previously that when we provided this type of information in an OCP forum. Here I'm just going to focus on the services and the controllers that are involved of the services and how they work. So NVM Express already ratified a TP 4165 LBA allocation with granularity. What that did was updated the LBA status commands such that you can actually read which LBAs are actually allocated in a namespace. So to do that, the hypervisor can send a command to the controller for the namespace that you want to migrate and say, hey, give me the allocated LBAs. And then, whoops, I'm sorry, I hit a button before I wanted to. I apologize. I did it again. All right, we'll do that again. So the controller is going to respond to the hypervisor and say, hey, here's the allocated LBAs that are reported to, that are allocated in the namespace. That allocation list will be on a granularity, but the hypervisor has the starting LBA and the ranges of all the LBAs that are allocated. Those can be converted to read commands to read the LBAs. The hypervisor then can send it over to the target server where he can then write the namespace static data. What's interesting is, why is this a separate TP from the TP that we're still working on in NVM Express? Is this particular feature can be used for things outside of live migration. So for example, snapshots. Snapshots where you want to snapshot a namespace, you can now just read the allocated logical blocks and not have to copy the whole namespace. So once we got the static view of the logical blocks, now we have to look at anything that happens for the dynamic changes, and we'll look at logical blocks first. This is a case where you have locally attached PCIe SSDs, and they're running, and you want to keep track of the changes that are occurring by the VM you're trying to migrate. So the first thing that has to happen is the host needs to create a migration queue within its memory, and then send down a command to the controller attached to the hypervisor and say, hey, I want you to create, from the controller's point of view, a migration queue. That command is going to identify the controller to be logged. In this case, there will be association to the controller attached to the VM we're migrating to that migration queue. This migration queue is going to look just like an IO completion queue in terms of its pattern. There's going to be a head pointer, which is what the hypervisor is going to use to collect the changes of logical blocks, and a tail pointer where the controller on the hypervisor is going to push changes in to that queue as we go forward. So what's going to happen then is that hypervisor is going to say, okay, start logging. So just because you created it doesn't mean you started logging. So now the controller on the hypervisor knows that I have to track the changes that occur to the controller on the VM. Now, NVM Express is not dictating how implementations happen. How you implement the logging is up to the implementation, but I'm trying to show how the API is used per controller and who's controlling what from the host perspective. So now when a write command occurs on the VM, and those writes get put in new allocated logical blocks, for example, in this example, get written to the namespace, those changes are going to go to the controller, who's going to push the LBA changes into an entry of the LBA changed at the tail, and then the tail pointer is going to move down. At this point, the hypervisor can see in the queue, there's going to be a mechanism to potentially get an event, or they could be polling the queue to say, hey, I have data in there. There will be a phase tag bit, just like with the IO completion queue. Then the host can come in and say, okay, I've read the data from there, and send down a message that says, hey, I've read the data from the queue, and it can also indicate where the head has moved down. And that's how the management of the head and tail move. I only showed one LBA. You can assume multiple LBAs are occurring because the VM is still doing potentially a lot of logical block changes to the namespace. The other thing that we're putting into this capability is to have the be able to track the changes that are occurring to the VM due to commands being executed by the controller on the attached to the VM being migrated. And those commands could be either admin commands or IO commands. This is a use case came in from controllers that may have a DPU for NVMe over Fabrics use cases. So what happens there is a command is going to come in and says start logging. And in that start logging, there's going to be memory ranges that say, hey, if that controller that I'm migrating touches memory in these ranges, then I want you to log it. I want you to aggregate those changes to me. When I ask for them, report them to me. And then as an IO read comes in, the controller is going to go ahead and push those read out. And if any of those writes to the VM memory are associated with the tracking that has been turned on, then what happens is later when that hypervisor comes in and says, hey, I want to query the aggregated changes, then those changes that were aggregated can be put to the hypervisor to say, hey, here's the addresses that have changed that you've requested. Now, I showed that data coming from the controller attached to the VM. How the NVM subsystem implements it is up to them. I just wanted to let you know that the actual data that is going to go to the hypervisor is due to VM writes that occur on the controller attached to the VM where the tracking was asked to be done by the hypervisor. And then finally, you have to get in, and there's going to be a command that says, hey, I need to read the controller state. And that controller state is for the controller attached to the VM, but it's the hypervisor asking the controller attached to itself. And when you ask for that, there's going to be two pieces of information that come across. We're going to have defined NVMe state, which are defined NVMe objects. And then there's going to be a way to do vendor specific state. Because there are things outside the NVMe spec that may need to be done. The way we've done it is we're going to allow things outside the scope of NVMe to define what the vendor state is. And there will be identifiers to say, hey, here's this identifier for the vendor specific state, and other specifications or customer negotiations with vendors can define what that state looks like. And then finally, you have to have a command that says, okay, pause the controller. And when you pause the controller, what's going to happen is that controller is going to stop fetching commands out of the queues. And then any command that was already fetched is going to be processed to completion. And after it's done, the controller is essentially paused. It's not actually doing any more commands in terms of processing. And that's really the end of the services that we're going to provide on the source side for doing migration. So now let's go look at the target side of what we have to do for services over there. And now that we've gotten the controller state, we have to be able to set the controller state. So in looking at the server of our target server here, I'm showing here that it has a hypervisor controlling the VM live migration management. I'm starting with a case where I have a controller that's paused, and it may be in some state in terms of the host that's attached to him. However, I am showing that the namespace has already been migrated here. I'm assuming that the static view of the namespace was sent from the hypervisor to the source to the hypervisor here. The namespace was created, and then all the data was moved, went through the whole migration queue and pushed in all of the LBA changes. So at this point in time, all the LBA changes are there. So this namespace matches the namespace that was done on the source. So we're going to focus, and so that's why there's no services over here, because all that writing is done by the hypervisor using existing NVMe commands. So now we're going to add a command that says set the controller state. And when that comes in, I'm going to turn this thing purple because it should be set to the same state of the controller that we migrated from. And I'm also assuming that this controller is already paused, so it's not going to be fetching commands. From an NVMe point of view, the state has been moved over. And so now we can resume operations. But now there is this thing called the VM that I have in orange. Now it's up to the host to migrate the VM from the source server over to this one here and making sure that it's at the state where it last left off. And I'm not talking about when it pauses or anything. That's all up to the host because we're focusing on the NVM Express point of view here. So we're adding a command that says resume. And when that command comes in, it can resume. The controller starts fetching code, assuming that the queues were pulled over from the VM, and we just continue where we left off, and we start processing commands and going into the IO completion queues as those are being completed, and the VM has been migrated. What I'm not talking about is what happens to that pause controller on the other side. The host, it can be reset and reused for something else, kinds of things. The other thing we're also doing that I didn't talk about is you can do pause and resume just to pause and resume and not migrate. That's an allowed thing to do in case you choose to change your mind as you started to migrate. You pause, you can say, now I want to keep running. You can do those kinds of operations. As I said before, we're trying to keep using existing commands. So like for the namespace, all the reads and writes of the data is using existing read-write commands. And I just want to make sure that everyone's clear that all the transfer of data from one server to the next is not part of the NVM Express specification. That's going to be out of scope. It's up for the servers to do that and to manage all of that themselves. The last thing I want to say is we're getting ready. It's getting close to being ready to be completed in terms of its technical proposal 4159. And once it's ratified, I plan to present at the OCP Global Summit, if they accept me to bring in the actual ratified, actually discuss all of the actual names of the new commands, talk about the events, resets, and all that other stuff that goes along with it in the future. That's why at this presentation, I can't give you all of that because I have to wait for it to be ratified by NVM Express. So with that, that's the end of my presentation. Is there any questions?
Lee, are you able to see the questions and read them?
Yeah, just trying to get back to the mute button here. Here we go. So from Pankaj, can controller states be organized in time order, or are they unordered IDs?
The controller state is the state of the controller. Typically, the way this is going to be used is go get the state once it's paused. We are going to allow you to get the state while the VM is running, but essentially what's going to happen is you pause the controller and you say, give me your final state and migrate that over. So in terms of time order, there is going to be nothing defined by NVMe from that point of view. And if you're going to read it while it's still live, you get the state at the time the command was done, assuming that that may be used more for vendor specific operations than the NVMe state, because we are going to be putting in the IO controllers queues in there, and they're going to be changing as you go along with that.
And there's a good segue to Stephen's question. What is the use case for having the concept of vendor specific state for live migration when there is a good chance the migration will be across different vendors?
So we are going to define a certain part of the NVM state, and if there's any state missing, it can be put into the vendor specific operations as to what can be done. It's going to be left up to the host to say, hey, if you're migrating from one vendor to another, hey, how am I going to align them up correctly in terms of, can I do it across there in terms of different features being supported or whatnot? We're assuming that, or the host can modify the data that's going across, because when they do the read, it's all public what it means. They can modify the things and take things into consideration when they're going between vendors, but that's right now outside the scope of NVMe. We're just going to say, here's this state of this controller, and you can set the state on the other side. My expectation is we're going to have additional changes in the future, but again, this is called the infrastructure to adding more stuff in the future.
I think also another use case I can see here is that, again, the DPU use case where you know, the devices on behind the DPU might be different vendors, but the DPUs are all from a given chip company or whatever.
And the other thing on the controller state is it may be very large, and it may have to do across with multiple commands, and we've taken care of that as well. Okay. All right, I stopped sharing, Ross. So
Great. Okay.
Thank you all.
We will go to FDP now. Okay. Hopefully these are all presenting the right view, I hope. So
Yep.
FDP. So we got a whole bunch of great speakers here, and how about if we continue on our journey here? And I guess I was bad and I forgot to turn my camera on, so I apologize. Open source update. First thing is Linux kernel. It has full support for IO pass-through. XNVMe has full support. QEMU has full support. FIO has full support. NVMe CLI is all upstream, and CacheFlip has been updated. So that's our open source status of what is there today and available for everybody to use for FTP. And with that, let's go to Keith.
Yeah, thanks. Yeah, I'm Keith. I am a Linux kernel engineer with Meta. And let me just talk about the Linux enabling effort for FTP. First, I just want to show just a quick high-level overview of the Linux storage stack. The whole point of FTP is that write commands can be tagged with placement hints that can be sent to the SSD for very smart placements. Now, when we look at the Linux storage stack, there's a lot of different paths and subsystems write commands can go through. So it has to be very carefully managed to do this. And as Ross mentioned earlier, the support for this is only for IO pass-through at the moment. So enabling this through the rest of the stack it needs to be carefully considered. So if we can go to the next slide, please. Okay, so the write hints, generally speaking, the application is going to have the best idea of what kind of write hint should be applied to a particular command, whether like the data is going to be very cold or very hot. So that's the layer that needs to be done. So the problem that we have at the moment, though, is that there isn't a generic interface that connects to the NVMe driver where the write hints can be sent through. Next slide, please. Now, if the NVMe driver were to have the hints, it's no problem. It's very easy for the driver to just pass it on through the SSD. The problem is, how does the application get that hint to the driver? We had actually done several things in the past with this. The write hints can be threaded all the way through to this, but that was actually removed several years ago. And it was only just a couple months ago that the write hints were placed back in, but that was done for a completely different use case for SCSI devices. So we're not quite wired up for it yet for the NVMe driver, but we have wired it up for a different use case. Next slide. So we've always had a pass-through interface with the NVMe driver. This goes through an ioctl. What this allows the user to do is they can craft whatever NVMe command they want in user space, and then they can bypass the entire block stack and just inject it directly into the driver, which then sends it to the SSD directly. Now, the problem with ioctls, though, is that it's a very synchronous interface, and it's not very fast. So we need a different interface. And then that's where a new interface called IOU ring comes into play. This was initially going to be pretty much a generic read-write interface, but it had recently added support for pass-through commands. And this can be done extremely fast. You can batch things up in a very optimal way. And similarly to the ioctl interface, the user can craft whatever command they want. They can attach whatever hints they want into it. And then the SSD will get it directly. So that helps a lot for applications that are able to use the raw NVMe interface. There are reference implementations using this in FIO. As Ross mentioned, CacheLib is successfully using this as well today. And as I mentioned before, there are ongoing investigations to make these file systems friendly. We are leveraging as much as we can from the SCSI interfaces that are already taking advantage of what the kernel infrastructure provides. And what that does provide is it provides 5 different write hints, which correspond to different levels of data hotness. FTP can certainly have a lot more than 5 hints in many cases. Right now, the kernel can't really support that because we're out of bits and the IO structures that we're threading through the kernel stack. But we also have ideas where we can use more hints for in-kernel use cases. So like file system metadata, they can have journaling metadata or B-tree metadata, and those would have different write characteristics than user data. So there's a lot of investigation going on here. This is actually happening like as we speak. We have patches outstanding that need to be reviewed, and hopefully we can get this added within the next merge window, which would probably be 6.11 in about 8 weeks from now. So that's the current state of things, and it's moving very fast. And it's looking like it's very successful since we're able to measure the WAF as a result of turning it on and off. So it's looking very promising. And yeah, that's it.
Thanks, Keith. Okay, Javier, you are up next.
Yep. So thanks, Keith.
Sure.
So hanging out here. So, Keith talked about the Linux kernel stack. I want to step back a little bit because, one of the questions that we've gotten as we started standardizing FDP and pushing patches into the kernel, one of the critiques is, we've been trying to solve the same problem for almost 10 years now, right? So we had these, we had block devices the NVMe standardized streams as directives, and there was actually code in the Linux kernel being merged, and there was code into databases like RocksDB actually being merged to use this. But at the same time, the efforts on Open Channel that we were doing to bring this all the way to a host-based FDL happened, almost in parallel, and that trend kind of catched on. We realized that it was a difficult interface to maintain, especially as we move from SLC NAND to MLC, and in TLC it becomes almost impossible. But in any case, Open Channel never got to be standardized in NVMe, so that was a real problem. Then, based on Open Channel, we went back and standardized zone namespaces. The promise was to do something similar to Open Channel, but bring it closer to the reality of NAND. And, just to put it at a moment in time, this is at the time where TLC started to come in. We started to have several layers. So the NAND from different vendors looked significantly different. So a more standard interface that resembled what was happening in the hard drive world with SMR was relevant. And, I think we've been like 4 years standardizing ZNS. It is through NVMe. There has been significantly efforts in the Linux kernel and in several applications, Ceph, some work on RocksDB. While that effort has been successful, we do see that several use cases for customers find it very difficult to adopt. This is particularly the case because the interface forces sequential writes, which is very good if you want to target a more cost-effective, reducing DRAM and all those things. But it kind of departs from the original use case of data placement, because you can actually place data without writing sequential to the NAND. That's not a requirement. Also, it was a very vendor-driven technology. So we didn't really have at least speaking from Samsung's perspective, we had some use cases in mind, but we don't own the workload, right? So that was also an issue when we tried to make decisions on how to use CNS. Now, FDP came from the other side of the world. So Google and Meta both doing different things, kindly agreed to align in the context of NVMe standardization, and try to focus the problem on strictly data placement. Now, the reason I'm telling this story is that one question that we get is you've done 3 iterations. What prevents you from FDP not working and then moving to the next iteration? So the reason I'm personally optimistic about this is that it goes after specific workloads, and we've seen that with CashLib, because it is customer driven. The changes to the software ecosystem after being, we've been involved in Open Channel, ZNS, and FDP. The changes to the ecosystem are not as intrusive, so they're significantly easier to adopt from an application perspective. And most applications that already have a conscience of being some sort of flash friendly, or whatever that is object-based, already has a concept of sizes and maybe some hotness. So it's very easy to get into place. So I think we can go to the next slide. Yeah. So the point I want to make here is, when we focus on data placement, what people is about, goes after. And we talk a lot about WAF, and I know that the audience attending the OCP are very familiar with WAF, but it's still a strange concept, because WAF is primarily used as a proxy metric that is very overloaded. It talks about space amplification. It has an impact on performance and latency. It has an impact on device utilization. And as I tried to make the point before, between CNS and Open Channel and now FDP, there's a component of engineering effort. The reason this happens, that is a proxy metric, is that write application is basically caused by the garbage collection that the device is doing due to the NAND characteristics. So the more garbage collection, the more write amplification, but the more interferences you're having to your user workload, right? So you're not having these super tight latencies. You might, depending on the controller and whether it's enterprise or cloud, your performance might go down. It's a very complex, the FDLs are very complex, and WAF is kind of this proxy metric. So the way we try to explain what's the value for this is, we have several customers that do not accept a WAF that is above a certain number. You know, in this particular example, I'm using 1.3. And so, and for that, they might over provision a lot. You know, we've seen over provisioning of over 50%. You know, some people might over provision at 60, 70% to reach those goals. The question is, how far down can we bring the WAF at that exact utilization point using FTP? And we can bring it significantly down. But the thing is that it's not how much down you can bring it, because your application can tolerate more. So the point is, if you increase the utilization of the device, where do you intercept that WAF? And that is free storage. So that's what we're after. We're not that much after cost of reducing DRAM. We're not about using some particular type of NAND that the writing sequentially would enable you. We're just after this WAF, primarily to give you the utilization at the WAF point that you are able to tolerate. I hope that makes sense. I think we can move forward, Ross. Yeah, I'm not going to cover this. Keith covered everything. So yeah, Linux, you can use it as it is today with CashLib. Things look pretty good, and we're putting patches on for file systems. This is the data with CashLib as a case study. We collected this, you know, together with Meta, and what this shows is that with very simple changes, there you have the pull request is already merged, but you can look at the code. It's a very simple code, reusing the existing CashLib separation of small objects and large objects. We can bring WAF down significantly. So what's interesting here, why CashLib is a very good use case, and you know, people in the call can try to extrapolate this for your workloads, is that we're making changes to CashLib on what you can call the storage backend, but the CashLib serves several applications, right? The API for CashLib does not change. So your actual application, your key value store, your object store, your whatever is not modified. All happens within CashLib. So you're getting these WAF benefits without having to go and modify your probably legacy applications you might not even have code for. Now, can we do smarter things? Definitely. You know, we can change we can change applications. We can try to nip it in aligning better to sizes. We can use the logs that we're getting back to be smarter, but that all add up in the engineering effort that you're putting and micro optimizations for particular workloads. So I think experience has told us that maybe stopping at this 80% effort is pretty good, and that's definitely what we're going after with the first wave of implementations. And I believe I'm not speaking only for Samsung. I think everybody has been building drives for a open channel CNS for a long time. So now we got at a point where we want to deploy something that people can utilize. Here you have another example with RocksDB. Just wanted to show that this is not particular about CashLib and super special. The changes to RocksDB for CNS are very aggressive. The changes on FTP are very minimal, and this is because we're using pass-through. But if at the moment the code gets into the kernel with the right hints, actually RocksDB is already enabled, because back in the days RocksDB was enabled for streams. So that will basically come for free at the moment. And I think that's it.
Okay, thank you. Luca, you are up next.
Thank you, Ross. I'm Luca, I'm from Micron, and I want to look to FDP from a different angle. Most of all, what FDP can do for large SSDs. So what is a large SSD? 64 terabyte, 128 terabyte, larger. May seem very large, but these things are coming and we have to be prepared. So what make large SSD special and why FDP helping? Well, what make them special is that historically in SSD there's been a ratio between the capacity of NAND and the capacity of DRAM to keep all the map and performance and all the consequent metrics aligned. And this mapping is going to break. The reason is very simple: is DRAM capacity cannot grow as fast as NAND. And even if it could, the cost is becoming prohibitive. Cost in dollars, cost in real estate, cost in power. So this pillar is going to tumble. And, breaking this pillar is like opening a Pandora box. The devil will come out. So everybody's care about that. So what we want to mention over here is how FDP can help. So first, looking at is the devil that bad? And the answer is no. He's not that bad, but he's still a devil. So he's something to deal with. And two, how FDP can keep the Pandora box still locked and keep moving on. So the main issue here is that we have to change all this mapping and this direction and the perception that the people have. And I keep using the word perception because that's the key, is that if we multiply the IU from any factor, the write amplification will grow accordingly and the life will decrease accordingly. And that is bad, most of all for SSDs that are based on because they're large, on QLC or PLC or what else, cells that are already weak in nature. So life is already an issue for them. So for example, we'll use as an example here 16 kilobyte instead of the standard 4 kilobytes, so a 4x larger IU. People have the perception that the write amplification will be 4 times worse and life will be 4 times shorter, and not to mention performance and quality of service implication. Can you go to the next slide, Ross? So let's look from the first angle. The first question is the devil that bad? No, it is not. So here is a table. We won't go into the details, but this table is a lot of benchmark run of a number of configuration, very repeatable, very auditable. Each line has between 10 and probably 200 million data points. So it's a pretty big set of benchmark. And these are just a reference. We have many more. And the idea is that the first line tells you that if you have a purely 4K random write, that what is people fear, look to the last column, the write amplification that you get on top of whatever is already based in the system because of the large of the 16K U is 4x. 16K instead of 4K, 4 times bigger. Write amplification is as expected 4x. Fine. Now look at all the other line. Those are real benchmark, that we ran. If you look to all this write amplification, all the numbers start by 1. Most of them start 1.0, and is only the second decimal. So the write amplification is there, additional, is not that bad, and maybe a 16 kilobyte is tolerable. But if you look to larger, it's getting worse. Like I don't have the column here, but a 64K, I think the worst is close to 2. Remember, 2 means half-life. Maybe that's not acceptable for some applications. So the problem is there, but it's not as bad. Instead of 4x is only 1.1. Instead of 16x at 64K TU is only 2x. So it's still a problem, not that bad. So how can FDP help in reducing this further? Next slide, Ross, please. So here is a simulation of some cases of FDP. Basically, we have 4 different applications. Running either on separate namespace that are mixed up in the same SSD as the conventional SSDs, and then the same one run in a in a FDP simulation, fully isolated mode or persistently isolated mode in this case. And we run 3 different type of benchmark. One of them is using FIO, using sequential pattern. Sequential pattern, people think they are over-optimistic. Well, yes, but not that much, because reality is a lot of sequentiality. Then we run with the JEDEC, JESD219A, which is one of the benchmark that is used for characterizing the life of SSDs and provide the drive write per day. And then we run with real benchmark, Aerospike. There is some description here what it is. And if you look to the next slide, we'll see what is the impact of them. So if you look at them, look at the table. In those configurations we created, if you look to the FIO, the write amplification in that specific setup is, conventional SSD is 1.63, with FDP goes to 102. With Aerospike, I skipped the JSD for a reason, I'll go back later, goes from 1.84 to 109. So they are sort of similar improvement, 37%, 41%, but actually this is even misleading because the baseline for WAF is actually 1x. So it's not 1.84 to 1.09 minus 41%, is that there is an 84 84% increase versus a 9% increase. So actually is a 900% if you want the right amplification improvement. So FDP by itself is helping reducing the contribution of a WAF of this application, no matter what, even with an existing 4K IU. But the 4K is obvious. Everybody's talking about that. You see everywhere. But this one, combined with the reality of how they work with very large IU, makes a very large SSD very usable in reality. What is bad is look at the JSD. It's 3.95 that goes to 3.8. It's minus 4%. The perception that is driven by that is that the right amplification is very bad. The reality that is driven by application is much better. It's not perfect, it's much better. And FDP, by the way, is phenomenal helping in real life application, way more than on reference benchmarks. So if you go to the last slide, just to close, Ross. So FDP, we see it as a key technology for a number of reasons. We've discussed, other people discussed about CacheLib and RocksDB and so on, but it has also value in enabling the very large SSD ecosystem and to finally get a disconnection between the NAND size, or a better improvement between NAND size and DRAM size, which will be key to make this device usable. And that is it. Thank you.
Thank you, Luca. David, you're up next.
Hi, thanks, Ross. So yeah, today's my topic is overcoming challenges in enable FDP in high capacity QLC SSD. Yeah, I'm from SiliconMotion. So yeah, about the challenge. So first, we think the FDP is ideal for accelerating QLC adaptation in data center or primary storage application, enabling high capacity and a low $ per gigabyte SSD. The reason is, FDP help dramatically reduce WAF and improve the DWPD is data write per day, and maximize performance while minimize the negative impact of the low PD QLC. This table is shows some merge data based on the 16 terabyte QLC SSD with the QLC NAND, the PD cycle 1500. So from this table, we can see as the WAF decrease, the IOPS and the DWPD inversely increase. So with FDP, if I assume the WAF is 1.5, I think the performance data is 450K. This data looks not bad, even comparing with the TLC SSD without FDP. Okay, at the same time, we see a wide range of design challenges in the high capacity QLC SSD. Yeah, we will focus two in this slide. The first one is how to reduce the FTL DRAM footprint to save the BOM cost. The second one is about how to manage the limited controller write resource for multiple handles. Next slide, okay. Just let's talk about the design or reduce the DRAM footprint. The design number one, use the configurable IU in QLC SSD, especially 16K IU for large size drive. Number two is a controller use a hardware assisted bit pack L2P entry for further saving L2P table size. For example, we use a 33-bit entry instead of 40-bit entry to address 8 gig IU. We can further reduce the L2P size up to 70.5%. Yeah, from this the table in the right side, we have 4K IU, 8K IU, and 16K IU. So So with 14K, 60K IU, it is feasible to implement 16 terabyte, 128 terabyte SSD with 32 gigabyte or 15 gigabyte as 32 gigabyte DRAM. The number 3, as Luca pointed out, small write on large IU will cause extra warp. So how to reduce the warp caused by the small write on the large IU? Our design support both handle with 4K IU and handle with 16K IU. So in the same SSD, so application can place the small write to the handle with the 4K IU mapping. Yeah, the diagram below is to show we have large IU mapping and 4K IU mapping, 2 group. Okay, let's move to the next slide. Another issue is a QLC coarse-fine program scheme with a couple word line program interval. Usually need a few hundred megabyte write buffer. So especially in the multiple handle case, SuperCap cannot protect the write buffer during the surprise power loss. So our design, the first option is we use the write flow with SLC copy back for the multiple handle QLC. So we support the 8, 16, 32 handle with read protection for the die failure. Yeah, design number 2 is we support the performance shaping engine to regulate the per handle write throughput, appropriately allocate the write buffer per handle. So this design is kind of help smooth the performance fluctuation in each write handle. Okay, next slide, please. Yeah, just summary. So the FDP bring down the WAF and make a high capacity SSD with low PE QLC NAND viable. So yeah, where 16 QLC SSD can achieve 1800 to 2900 megabyte per second write, and the DWPD 0.6 plus on the FDP aware application. So high capacity SSD, QLC SSD requires more design optimization on the DRAM reduction and the write resource management for multiple handle. So yeah, our design method is we talk about 3 aspects: is reduce DRAM with large IU and the compact L2B entry, and the support coexist handle with 4K IU mapping and 16K IU. So yeah, our write flow support SLC copy back and do the performance and the QoS control among the different handle. Okay, just pretty much my side.
Thank you. Thank you, David. John Michael, you're up next.
All right. Hey, I'm John Michael Hans from FADU. I'm going to talk about FDP, like the other guys. Although this is kind of an overview. I think you heard from everybody that WAF is bad, but what is write application factor? And it's very hard to optimize anything for SSDs if you don't know what WAF is. But WAF is bad because you're writing more data to the NAND, to the SSD, than the host wrote. So when the host writes data, then the SSD has to write more data because of background garbage collection. Just the way that NAND works, you have to erase in blocks and you program in pages. So WAF is bad. If you can improve the WAF, as you've heard, you can increase not only endurance, but also performance. So what is FDP? So I think one of the big key insights is basically you can flexibly place data, hence the name, based on these different RUHs or reclaim unit handles. And basically you can do it at the granularity of an erase block. And the drive that we're going to be looking at with the FADU drive, we have one TLC SSD we have 2, 4, 8, 16 terabytes, and these are going to have 8 RUHs. and each RUH is striped across all 16 channels, and there's 4 die, and this is this thing called a super block. But if you can put the data all together in these super blocks together, you can get improved isolation, which improves quality of service, it improves the performance, and the endurance. So the WAF is modulating all 3. We'll also talk a little bit about the TCO, but one of the really big key differences, and Javier touched on it a little bit, is that it's fully backwards compatible. So that was one of the challenges with something like ZNS, where you have to have a lot of software development to support something like ZNS, where FTP, it may be very small changes to support the write heads. And you'll see one of the use cases we have is just creating multiple namespaces that are fully aware of FTP, so you don't actually have to do any software development to get the benefits of FTP. Obviously, if you reduce the WAF, then you don't have to do any over-provisioning. Over-provisioning is really just, the only reason anybody uses over-provisioning is to increase the random write performance or endurance. And if you have a low WAF, over-provisioning doesn't do anything. I get asked this a lot from, hey, should I buy this 3.84 terabyte drive or this 3.2 terabyte 3 drive write per day drive? Well, if you have a WAF of 1, you're wasting money by buying any kind of 3 drive write per day drive, because it doesn't do anything. And if you get lower WAF and you actually implement these drives when you're making these decisions, you can actually spend less money by buying a smaller capacity drive. Russ, next slide. Yeah, so this was from OCP last year, which we touched on the 2 use cases. Javier touched on, the key was that it was developed Google, Meta from the end user side, and then a bunch of SSD vendors. And CacheFlip is really interesting. Thank you, Javier, and the open source team. Like, they helped us get CacheFlip up and running with FTP. And I can't understate, so if this is one of the main use cases for small capacity TLC drives, which is caching and databases, and if a hyperscaler, for instance, had to buy an SSD that was 4 terabytes and over-provision it to 2 terabytes to get the right WAF and right performance for their workload, and now they can buy a 2 terabyte SSD, they've reduced their flash costs by 50% in the server. So this has a massive impact on TCO. And if you can deliver higher application performance because you have a lower WAF. So anything that has multi-tenants, multi-namespaces, multi-applications, I mentioned different write streams, VMs, containers, microservices, log structure, DBs, caching. There's a ton of really, really good use cases for FTP. And hopefully there'll be, this is the presentation that they gave at OCP last year. It goes through some of these a little bit more detail than we went through today. So CPU core counts are getting bigger. Intel has announced they're going to have like 144 cores this year, and then 288 cores, I believe, within the next 2 years. And the average capacity TLC SSD for compute use cases is going up accordingly, because obviously if you're running VMs and you need to have a certain amount of capacity for each VM, which kind of maps to the amount of cores. And so this increase in core count is driving the increase in TLC capacity for compute, which is driving the need for running a bunch of mixed workloads on these TLC drives. So the SSDs are going from 2 terabytes to 4 terabytes to 8 terabytes to 16 terabytes in the TLC. So this is just a really cool, very, very simple FIO test, 50-50 read-write workload without FTP and with FTP. And when you turn on FTP, your mixed workload performance goes up by 86%. That was that was that last slide. Ross.
You ready to go for the next slide, or you want me to go?
That's fine. That's the so that's the punchline. So especially in these ones where there's sequential writing and you can even be random read, you can mix that together. And if you use FTP, your application performance is going to go way up. Why does it go up? We talked about WAF. So this is another FIO use case where we just have 8 different write streams to the drive. So you have 2 that are 128K, 2 that are 64K. If you typically do a bunch of sequential write streams to one drive, it looks random to the drive and you'll have a higher WAF. You can see that with the non-FTP, that light green on the bottom. So if you turn on FTP, it goes to a WAF of 1. And you can see the throughput on this drive goes from 1,500 megabytes a second to about 5,000. This is a 3.84 terabyte TLC drive. So with FTP, you're getting like over 3x the benefit of performance, and you also get that back in endurance. So it's good for any applications where you can split up the writes into multiple streams. You can go to the next slide, Ross. Okay, so this was, you're going to hear more about, I know we're kind of running out of time, but we're doing some really fun experiments with virtualization. And I'm using here Proxmox, but I just basically used a drive. You basically delete the namespaces, enable FTP. You can create 8 new namespaces, and each one gets its own RUH. And so each of these namespaces basically will get its own, data that's initially isolated. There's two different modes. There's initially isolated, persistently isolated for FTP. But on this drive, we basically I just formatted each of these namespaces with an LVM, and I attached each one of these to each of the VMs. And basically they get through VirtIO a virtualized disk. And you can even provision the IOPS. Say, for instance, if you wanted to give that one VM 100,000 IOPS and another one 300,000. But the key changes here is that with FTP enabled, if you're doing a bunch of workloads to each of these namespaces, because they're attached to these VMs, they're not interacting with each other, and you get better quality service. So I have a full suite of Ansible tests with FIO and a bunch of cool benchmarks we did to basically show off the value of FTP. But you heard from some of the other folks that if you basically just split up the workloads and each of these VMs have their own little namespace and they're all isolated, then each of them are going to have a much better user experience because they get better application performance, better quality service, and the whole overall drive has much better endurance. So this is to reiterate, the value of this use case is that the applications are not FTP aware. There was no application development or no application changes required. Each VM just gets their own namespace individually. So I said no SRIOV here. In the future, if you wanted to use SRIOV or any other kind of virtualization to map the namespace directly to the VM, you could do that as well. But yeah, more on this at FMS this year.
Great. Thanks, John Michael. Appreciate it. I want to thank everybody on the FTP panel for all their presentations and great information. We're running a little behind time, and we are going to skip forward here to the Hyperscale fleet learnings. And I'll find the slide, but Vineet, you are up first in this section.
Sure. Thanks, Ross, for the shift in probably the changes in the schedule. We're going to talk about open source testing. Ross, if you can go to the next slide. I did want to introduce a few of the participants of the presentation. Myself, I'm Vineet. I'm a hardware engineer at Facebook. Ross, Jan, and Adrian have been my contributors in this journey for allowing us to basically make progress in our open source testing journey. Can we go to the next slide, Ross? Okay, so why is all this important? I want you all to imagine a world where open sourcing test becomes an innovation cornerstone, where our qualifications are much more seamless, and our vision here is not really grandeur, but just about some practical innovations and streamlining processes that fosters collaboration within the OCP community. The OCP community has long been an innovation, and we all kind of unite over here in terms of kind of defining this journey in moving forward, where we open source a lot of our stuff to help foster a lot of collaboration as well as innovation in terms of just the whole testing space in the storage world. Can we go to the next slide, please? Okay, as we dive into the current state of SSD qualification, we want to acknowledge the diverse approaches each hyperscalers take. Specifically in Meta's case, we used to have a tool called HiFi, which has its own unique framework and the own method of writing tests. And then, that tool would be used by different SSD vendors and trying to integrate that into their qualification process, which is a big burden for each vendor too, because they just not have to entertain us as a hyperscaler, but they also have many other hyperscalers and enterprise customers and OEM customers, which they need to basically deal with. And resource allocation, what we found probably through our journey with this is there was so much of resource misuse in this entire process, because you got to allocate teams within your hyperscalers at the vendors, and overall the process basically becomes much more lengthy and involves a lot of complexity as well as resource being spent on this work. Next slide. Okay, some of the things which we're keeping in mind in terms of, when we design a solution, right? Like, what are the things which we actually are trying to avoid, and also we are trying to take care of that when we are basically trying to go design this. So we want to basically make sure that, we acknowledge the efficiency problems which are going to be there because of something like this. The cost of the complexity, because each custom solution not only drains, the hyperscalers resources, but also burdens the vendors, right? Like each vendor has to now keep an infrastructure as well as, the processes of each hyperscalers in there. And, the catalyst for change, these inefficiencies highlight an urgent need that we all need to come together in terms of how do we improve in this landscape, right? And testing and debug is an area where it's not as cool as design and FTP and some of these things which are really important for us in the industry we talked about, but which always gets ignored as one of the after effect things and not get focused on. So I feel this OCP provides us a really good platform to kind of come together and improve in this area. So what's our solution? Ross, next slide. So Meta's solution here is basically to open source tests. And through open sourcing tests, we aim to harmonize the process, we aim to reduce the complexity, and we hope that this basically helps foster innovation, right? Because we're being much more open in terms of what we are testing and what we are looking for when we're trying to basically get some of these SSD devices. So what we propose here is an adoption of an open sourcing testing strategy that the SSD customers as well as the SSD suppliers and the industry in general can contribute and utilize. We hope that if we harmonize these testing procedures, we will reduce the need for all of these custom solutions. And even if it is, it's done in a much more open source format, so it allows us to have a dialogue and conversation in terms of adopting from each other's learnings in there. And we have this belief that an efficient qualification process will always lead to faster time to market, which benefits everybody in this journey and not just one. So, okay. With that, we have some announcement to make. The future, which I started with in the slide one, which was Imagine the World. For us, it has arrived. Meta's test framework and storage qualification tests are now available at the OCP GitHub repository. We have posted the links over here. I did want to highlight that this effort of OCP test and validation was started long back by the OCP test and validation community, and we have piggybacked on that work and effort by putting some of the tests as well as our framework out there. The OCP framework is pretty much the repository which we're going to be used to kind of in terms of how we write tests and how we design some of these tests. And if people wanted to create more tests, which Meta wants to adopt, and we want to run it in our qualifications, then it's important to understand how the framework is. The storage tests folder, which you see in there, are pretty much our storage tests, what we're going to run in qual. Next slide, Ross. Okay. Now, we're not just basically putting the repository out there. What we have done is we have tested this repository in our labs in a OCP environment server, which is basically connected off the Meta infrastructure. So we really wanted to make sure that what we put out there is properly tested and properly vetted out when we put it out there, so that when developers and SSD vendors and other hyperscalers and tool developers, when they use this, it's something which works. Next slide. Okay, I have a snapshot of basically what we have in there, so that I can kind of attest to what I basically announced in the slide before, and I'm not bluffing in there. So I have a snapshot of two repositories. On the left, what you see is probably the framework repository. On the right, it's the SSD repositories. We have basically put a selection of first few tests which we wished to go live with. I hope you all understand there's a lot of legal processes and stuff which we have to go through as kind of code goes out. So there will be a lot more tests which will be added in the very next few days. The goal is to make sure that our entire qualification tests and whatever we use at Meta will all be open sourced in there. And lastly, I did want to highlight that, sorry, can you go back to the slide, Russ? Yeah. Yeah, AutoVal, the framework which is on the left, will be compatible with the OCP test and validation specification in the very near future. We're trying to be disciplined and kind of follow some of the learnings of the OCP test and validation work group when we actually try to do that. So yeah. Okay, next slide, Ross. Okay, impact and future direction. So we believe that this will have a wide scale industry benefit. It'll basically help us to not only open source test, but also streamline our entire qualification process. But we also think that by sharing tests and all the hyperscalers and all of us kind of coming out there and putting it out there, will overall just improve the quality and reliability of the storage thing. And who wouldn't want that, right? In there. And I believe that the open source nature allows us to scale it, and we are much more flexible in terms of what we want to run, what we not want to run in there. And it'll allow us to basically do a lot more advances in even from the design side, because there'll be a lot of learnings from this, which we actually put in for all the new features which we are trying to design and what we're trying to do in there. And I hope that this is a collaborative success. Hyperscalers, OEMs, vendors, or storage developers, this basically can become a community-focused approach in solving some of the challenges we face in our qualification, debug, and testing world in there. Next slide, Russ. Okay, call to action. We invite all the industry players to join us in this initiative. I posted the link to the repositories in there. We certainly are not calling ourselves as the test experts, as the only test experts in the industry. So, and I hope there are many experts out there in this call as well. So we will basically piggyback on your expertise and insights too in making this entire thing efficient and innovative. Some of the things on how to basically get involved, you utilize the open source test cases across the industry. So whatever we'll be putting it out there, we will be doing a much more deep dive presentation. I think Ross will send out the details in the future OCP monthly storage meeting. I'll have my co-participants, like either Adrian and Jan, kind of come in and kind of we will dive into how the repository is structured, what are the tests, how do we plan to add more, and a lot more details in the next presentation in there. Participate in the OCP test and diagnostics effort. So this link is there. So if you want to basically talk about something which is outside of storage or so, there is a platform in OCP testing diagnostics. I did want to highlight it over here. And if you have any other innovative ideas when you see there, I don't think we are done yet. So reach out to me or Ross, and we would love to basically talk to you. So yeah, just the last final thing is join us in this open diagnostics and test innovation. We really hope that this effort of open sourcing and we coming out and kind of sharing our tests becomes like a cornerstone for seamless and efficient qualifications. So thank you with that.
Thank you, Vineet. Chris, you are up next.
Okay. Hopefully you guys can hear me. I'm Chris Sable. I'm a storage architect at Google. I just wanted to start with some very high-level thoughts here in general directions. The first being, the OCP data center spec, right? That's cornerstone of one of the cornerstones of our SSD strategy. It's super helpful to just align across all the players. Another cornerstone here is security, right? Our users trust us with their data, and that's one of the critical foundational pillars of our storage strategy. The here that I want to touch on is just qualifying and maintaining storage at scale is not an easy problem, and so we're continuing to look for efficiency in testing, maintenance, and handling the scale of devices. Next slide. Oh, I think we skipped a lot.
Sorry.
Yeah. Okay. So the data center specification. So what's the point of this? What do we see as a value? So the challenge here is just, I think there's a lot of disparate customer asks for NVMe SSDs, right? It's just this convergence point of storage across multiple industries. And what you hear from vendors time and again is, okay, you guys just need to agree, right? And I can't do this 40 different ways. And so what we have, right, is the OCP data center spec. That's our answer to that problem. We want to focus on one, high volume, well-validated solution. And this is kind of how, the contributors to this spec, we get together, we try and hash out our differences and come up with one strategy for things as much as we possibly can, or at least understand where the differences are, right? So specifically Google, I mean, we see a lot of value in, the FTP requirements, which have been, exist in the 2.5 spec, telemetry, and I think we've focused also in 2.5 on the security piece and just getting that dusting it off and getting it well aligned with everybody. So, the ask here is just, please support that OCP NVMe data center spec, and we thank you for that. Next slide. So then I wanted to get a little bit more into security, right? I think one thing that's not maybe clear, and it's maybe not the way folks normally think, but in this security space, in terms of trust, it's very opaque from a customer standpoint, right? We buy a drive, it's got an Opal interface, but we can't see the implementation of that. We don't necessarily know the quality of it. And because of that, an exploit on one SSD really, you'd expect that to mean that, that vendor had a bug, they have a problem, but everybody else is fine. But that's not the way that people think about, at least historically think about security. It's every time there's a bug, it's that just means there's bugs in other SSD implementations that we haven't seen yet, right? So this really gets interpreted as a vulnerability of all SSDs every time there's an exploit or an issue out there, right? So that really kind of points this out as like a problem we have to solve together, and something that everybody sort of has a vested interest in resolving. So, our strategy on this, at least over the last year or two, has been to try and remove some of that opacity. So we can really understand the quality of the underlying implementations. And so it's not the case that, if we have a high quality implementation, that it gets dinged because somebody else doesn't, right? So I think we kind of can break this into steps, but we think of, the first thing is just auditing, right? And OCP Safe is a strategy there. I think, a second step here is integrating Calyptra as a hardened root of trust that can, is open source. So multiple people can look at it. It can be audited externally, and we can really build that as a cornerstone of building, our trust models. Building on top of that Calyptra, though, then there's this initiative to do OCP lock, which I think folks are going to talk about. But this is really dealing with the SSD specific, or the data storage specific piece of the trust that comes with key management and some of the pieces exposed traditionally through Opal. And obviously, once that component, that OCP lock piece exists, the need to integrate that functionality in the SSDs. So we think of security as foundational. It's table stakes. That we got to work together, and we need it for circularity and just for general confidence in the SSDs. So next slide. So I think this comes back to kind of what Vineet, a lot of what's on this slide comes back to what Vineet was just talking about. But a year ago, I think we talked about our needs for maintaining storage at scale and qualifying drives, and we talked about needing more efficiency in testing, open sourcing tests, and we needed to also improve our debugging at scale, right? So looking at where we are now in 2024, Vineet just talked about this open source OCP test repository. Google is absolutely aligned with this, on board with it. We see a huge benefit here, right? I think Vineet didn't. I think we'd like to talk internally about shift left, which is this idea that in firmware development cycles, especially, the sooner you can run tests and find breakages in the development cycle, the tighter the loop is between develop and test and break and fix, the faster the velocity and the higher the quality of the product in the end. And this really lets SSD vendors integrate our tests closer in their development cycle, right? And since they're open source, there's nothing it can be adapted to environments that we can't support testing in, right? I mean, if they need to, right? Controller vendor can take these tests and potentially even translate them into RTL validation if they're needed, right? It requires that openness on it to be able to do those sorts of things. And then also just being able to build this repository as a common clearinghouse, so that it's we can take kind of the best of everybody's tests. Yeah, right. And I think along with that expertise externally, it's we love other people to understand how we test things, right? Because otherwise we get a breakage and we got to explain why it matters and what we did exactly and what the specific case was. If that expertise can percolate out into the wider world, that's a great thing as we see it. So, I think Vineet talked about the repository that exists. We're working on trying to finalize our first 3 test cases. So I think need to stay tuned on the Google side, but we're working on this. Next slide. Okay, that's me. I'm done.
Thank you, Chris.
Yep.
Lee, you are up next.
Yes, I guess future tip for me is don't go last, because it's pretty much +1 on everything Chris said. So can we start off again, pretty much exactly as Chris related to it, right? Security is table stakes. If something goes wrong with security, your reputation is ruined and you're pretty much out of business. So with what we've been doing over time within the spec itself, we are now in OCP 2.6 draft up to 120 different requirement IDs in the security section. So we're constantly beefing this up as we go. But as we say, security is a journey, not a destination. And so there'll always be more to do. Again, echoing what Krista talked about, safe. We're going to be requiring that for all firmware, both first level firmware, first drops, CS drops, as well as maintenance release firmwares. And so with that safe audit process, having the standardized audit and the output from that standardized audit as ability to go into the attestation systems within the fleet will be critical going forward. FIPS 140-3, that's kind of also one of those things. It's just making sure government-wise that we're all safe and correct. Calyptra as a root of trust, and now building on that log. So I think everything around here you can see is how do we start to get some of the more, stuff that's not differentiating to the SSD, that's just core root things that the SSD has to get right. Let's figure out ways to make that as simple as possible, and through that do open source blocks that allow that to always be correct and auditable, of course. Next slide. So resiliency. I know people have heard me say this many times. 1,000,000 to 1 chances happen 9 times out of 10 at scale. If you have 10 million drives, you've got 10 events probably daily out of some of these things. So we need to figure out ways to ensure that we minimize things that you would think was a corner case of a corner case, but again, at scale over time, you're going to hit all these things, and that's painful when the SSD has some sort of panic event, and then the VMs on that SSD crash. Customers don't like that. So, of course, increasing core counts and device size increases the blast radius of these things. So not only is it bad overall for a given VM, we're now starting to do sorts of things where tens of VMs or hundreds of VMs end up being affected if we're not careful. So with that, simple asserts saying panic just because I don't know what to do really don't cut it anymore. We have to be able to structure these asserts in a much more fine-grained way so that drives are able to recover in the least impactful way possible. And what we mean by that is kind of North Star would be to recover under the hood, do whatever you have to do, get it done, get us back to a running state, and just then tell us that something happened through controller-initiated telemetry. Now, of course, we know that that's not always possible, but the idea is to drive towards less and less impactful recovery mechanisms using the error recovery methods. Next slide. So, debuggability. Chris touched on this as well. We try and shift left as much as possible with all of our testing, and we're adding more test cases, and we're open sourcing test cases, and we have test plans. And all of that is great, but it's impossible to cover all the corner cases in something like CDL. Just again, it's all these different millions and one things can get pulled out somewhere along the way. So really the OCP 2.5 telemetry is an awesome way to start to be able to really minimize the debug turnaround time, because number one, it's human readable, it's configurable, it's expandable, the ability for vendors to tune with vendor unique debug events classes so that they can really hone in on the things that are specific to their firmware and allow things to then be able to be quickly pulled out of the data center, given to a given vendor, have them work through that and get a fix back to us as soon as possible. And so as Microsoft and Azure, we actually feel that telemetry is so valuable that we're actually going to be pushing pretty aggressively to already in-fleet devices that that we have in the fleet today. So this is not just for new things coming down the pike. This is, we want this back as far back as we can go. Next slide.
Okay,
That's it.
I think we could take maybe one or two questions. When we take questions, I will get our slide deck back to where it went. Mike, do you have a question for us? The question list?
There was a question on how is the Open Compute project related to the Open Hardware Group?
Yes. So they are not related. The OCP is its own entity, founded by Meta and added to by Microsoft and Google and others as we went along. The Open Hardware Group is under, I believe, the Eclipse Foundation, and kind of serves a separate role for RISC-V type architecture implementations.
Next question is, how does the SSD strategy interlink with the root of trust and trust forge being done by Agita Labs?
So OCP really, so Calyptra is really its own root of trust, open source through OCP. I don't think doesn't really, I mean, I guess they're orthogonal really, in my mind. I don't know. Anybody else have a anything to add on that?
I don't. All right.
Okay.
Let me know when I have running out of time. Next question is, what about the backlog for getting through FIPS 140-3 certification? The government is slow and taking a long time versus NAND life cycles.
Yes, this is a well-known problem in the industry. I think some of that, obviously, SAFE is going to help with that some degree, because we get some indication, at least from a good auditor system, that we have solid firmware. Also, at least from Microsoft point of view, we don't necessarily, the drive needs to be submitted for certification into the test house as part of our bring up and certification, but it doesn't necessarily have to have the certificate before we ship. It has to be on the journey.
Okay. Next question is, do we have a
question,
draft?
Mike.
Yeah. Do we have a draft of the version of OCP Data Center 2.6 for viewing?
Ross.
Okay. Sorry, my camera's not on. We are all working on getting a draft, and we're not there. But I think it's fair to say all the authors are working very hard on this and have strong desire to get it out. So anyway, thank you, Vineet. Thank you, Chris. Thank you, Lee, for the session. And Lee, you're on next here with
Again, I don't know.
dates.
Great. So next slide. So this, we want to basically talk about first the data center NVMe spec. This is going to be the 2.6 rev. Really what this is kind of a lot of stuff that didn't make the cut list for 2.5. So very much the intention here is to get those things put into a fairly quick rev, though now it's kind of we're getting a little bit of feature creep. So as Ross said, we're working on trying to get a draft together as quickly as we can. But some of the highlights that we're looking at, additions of our things like expanded air injection. You can see some of the ideas around what we would be doing for allowing, being able to inject an error into the device, having the device trigger events such that we can test both the device handling and the OS handling of events. Next slide. So one of the things, again, we telemetry, right? One of the things that some of the vendors have come back to us about saying, hey, 16K is kind of tight. Can we relax that a bit? And so we said, absolutely yes. So we really want you guys to be able to debug very easily. So we've doubled the size to 32K so that we can, there's more room for you guys to play in. And we've added sort of a virtual FIFO support, enabling greater than the 16 FIFOs. Some people felt that they wanted to have many, many FIFOs and they wanted to be able to construct those and change sizes into things. So we've added a lot more virtual FIFO flexibility in data area 1 and data area 2. Next, yeah. So one of the things we're kind of doing some clarifications. One of the things was we've talked about the devices to have a mechanism for making sure that the firmware isn't hung, but we never specified what that periodicity should be. And so we're going to be pushing for an interval of around 2 seconds. Now we know that's problematic for some people. Feel that's a bit problematic, but we want to be ensured that we have enough time for the device to see that it's hung, for it to do the timeout, for it to recover, and for us to get the device back up and running before we have multitudes of IO timeouts. Next. Again, as we talked about, we want all of the recovery from an event or an error condition to be as seamless and least impactful as possible. So we've just added some wording here saying strongly preferred the order of the precedence of how these resets happen so that we are at least impactful on the customer. Next. And security. So one of the things is specifically within 2.6, we are requiring a safe audit to be performed on all firmware versions and each firmware release. Next. So that's kind of all of the bigger things. There's clarifications happening with stuff that's being input from feedback, some additions from some of the folks like Dell have some things that they want to add in as well. And we're having some ideas around in the telemetry, do we want to do things like add something around workload tracking? Because oftentimes, at least from us, we get the debug information back to the vendor, and the vendor's immediate question is, well, what was the workload? And by the time we've done that, I have no clue what the workload was, and probably didn't even when the event was happening because it's the customer workload and not mine. And so do we need to add a mechanism such that the drive can kind of keep track of what's happening and what's the IO is and the pattern and the timing and something like that. So, kind of needs more discussion, of course, but these are some ideas around that. And so now flipping over, so instead of the NVMe spec, we're now going to talk about the SAS SATA spec. We have, of course, the 1.0 version is out, and we're now working on a was it 1.5, 1.1? We haven't quite settled on that, but we'll call it 1.x here. Next slide. So a lot of what we want to do, you can think of it as like, hey, all of the advancements we've done in NVMe spec since the introduction of the 1.0 SATA SAS spec, we should be getting that ported over. So main items are things like, of course, the telemetry, enable human readable debug logs. Of course, as we pull that we need to rework the transport mechanisms to fit with SAS and SATA protocols. Things like maybe we need to use it for SAS, maybe using a read buffer, write buffer. We're all looking at all these different things and how this stuff now fits in. And as part of that telemetry, NVMe, of course, is very much SSD focused. So are there HDD specific debug information that we need to standardize as part of that? Next. Or again, some sort of the security concerns about the TCG configuration and history logs. The TCG history we had in one version, we had the history log specifically as a separate log. In the NVMe side of things, we have now kind of gone away from that and pushed all of that into the persistent event log. But we need to have equivalents of that in SATA. So how does that get formatted in? Again, it's kind of porting to fit the protocol as we go. Next. And as I said, all those 120 security ID requirements in the NVMe spec, we now kind of have to make sure we're on par here over here on the SATA side.
Hey, Mike, do we have any questions?
Yes, we do. Can we work to get OCP safe, CLIPTRA, and lock included into the dataset security specification? I think you already talked about the safe. Lock is still in progress, so it's not completed, but you guys want to talk about CLIPTRA included? Lee?
I
Ross?
know that.
Lee, I think this one's for you.
It is. So CLIPTRA, we know, is a heavy lift. It's a core portion of a lot of the SSD security systems. Timings for different SOC and their tape out is obviously variable across different vendors. So having a hard time requirement for CLIPTRA is a little bit dicey at this point, I'm going to say. Frankly, from I think our point of view, CLIPTRA is awesome. Really, when it's going to be much more useful and part of something that we're going to push very hard for is when we have lock to go with it.
Mike, next question.
Yeah, will the SAS SATA spec have similar telemetry log size requirements as NVMe? 32K question mark.
Yeah, I think, as a starting point, that makes the most sense. Obviously, from there, we may need to adjust things depending on what vendors find useful and needed.
We had an earlier question that was about my presentation about live migration, and I accidentally hit the answer live, so I lost the question, and I wanted people to hear the answer. And that is SROV included in supporting live migration? Live migration is going to support any type of NVMe controller. So if you have a bunch of physical controllers, or if you're using SROV, live migration will be supported. And the next question is, do we have a draft version of the SAS SATA HDD R1.X version, the next version, available?
Not at this time yet. We're just kind of getting rolling on that. So it's going to take us a couple of months to get stuff built up to the point where a draft would be useful.
Now
Lee,
we're going to go.
let me add to that.
Yeah.
There are a lot of Dell requirements, and as they've joined the spec, and so those are in progress of getting into the spec.
Yep.
All right, we're done with this section, but we do have an FDP question that was done earlier. See if somebody could answer it. How much does the success of FDP hinge on the extent of its implementation by individual applications?
Does anybody on the FDP panel want to answer that? Otherwise, I'll answer it.
Go for it, Ross.
Okay. It is not. So FDP, what's interesting about it is if you have an FDP application knows about FDP, it obviously has high benefit. If you have an application that does not know about FDP, it will still benefit from this. You saw that in John Michael's slides where he just created a bunch of namespaces and the data was associated with the namespace. In that case, those applications had no FDP knowledge, yet they had high benefit. Are we good with questions, Mike, or should we go to the next?
There is one more question.
Okay,
The question is the release of the OCP data center NVMe SSD specification 2.6 expected to be ready by OCP Global Summit 2024?
Lee, you're quiet. I guess you went this wrong. The answer is
well.
we're trying to achieve that very hard.
Yes.
But I don't want to promise people and let people down.
No.
But there's
Yeah,
strong
I
desire.
was going to say, I bloody well hope so, but yes.
Okay. With that, Steve Wells, you are up.
Okay, hopefully I'm off mute here. Looks like it.
Yep, you're good.
So resiliency has been a North Star since OCP version 1 spec, and it has improved over time. And so a year ago at this conference, even though the 2.5 spec came out in September, a year ago at this time, the OCP committee gave me distinct privilege of discussing telemetry and everything associated with telemetry. And as you could hear from the prior conversations, telemetry is a really important ingredient both for monitoring and for efficient debug. There is a bigger picture for resiliency that's also addressed in the spec, and there are some specific enhancements that were added to the 2.5 specification around resiliency outside of strictly the telemetry conversation. It's worth the conversation. Let's have it. Next slide, Ross. So if you look at the standard projections that you would get for a 2.5 million hour MTBF, it seems like a good number until you start looking at a large fleet. I kind of used as an example right around 15 million drives. And if you kind of look at that, the failure count is a significant number. And sorry, from an FMS 2023 from Microsoft did a presentation on a vision for what they call vertically integrated high resiliency, which is a collaboration between the host and the device. And they picked a new number down there. By the way, that kind of works out to about a 10 million hour MTBF equivalent. And this is all done by the enhanced robustness that Lee and others have communicated. And there's some specific language in 2.5. There's going to be some ongoing language improvements in 2.6. And it's worth kind of spending a little time talking about. Next slide. So shift left is used. Our view of shift left, I think, in the resiliency space has to do with rather than just having a drive fail and assert, at least we have some method of recovery, and that's been captured in the OCP spec since early on. Rather than having to deal with asserts and recoveries, is there a way to proactively detect these problems? And beyond just proactively detecting these problems with enough fleet monitoring and maintenance, maybe we can find ways of preventing some of these problems. As a device vendor, there's a very likelihood that if we get large amounts of fleet telemetry data, we can then analyze that data and potentially put some better screens in place in a component factory or an SSD factory. We can bake in additional capabilities in future generation NAND lithography or SSD design. And so there's a lot of really good ingredients to be had in this shift left. As a quick analogy or a data point I wanted to share with you, I have a colleague of mine who, as an intern, that actually wrote firmware for Formula One. And we were talking about asserts, and he went, "You do realize that Formula One cars don't have firmware that asserts for obvious reasons." it's keep going. You know, there's no, it's far too dangerous to obviously assert the controller in a Formula One vehicle while it's running. So the idea is that you just keep going no matter what. You recover the best you can, and then log that information so that you can address it in an efficient way. Given that, next slide, Ross. Take this to another example, which is what happens in your automobile. Rather than a panic in your automobile, you typically get a check engine light. And if you notice the check engine light is not red, as in you better pull off on the side of the road this minute, it's yellow, which is you should deal with it when it's appropriate. And then to the topic that we discussed last year, then what we typically do is take the drive to a shop. There's a standard connector that works on Hondas and Fords and Prius and Teslas and everything else. You can plug in that standard port in a standardized way. It has vendor unique information inside of that telemetry that's outputted, but it's with that telemetry then you can go determine what the root cause of the problem is in next steps. So the idea that we're visioning for is we want to get more into the check engine light than we want to get into the halt and panic that we've had in the past. Next slide, Russ. So a bit of history that we've dealt with in around this here. So even pre-OCP1, there was a lot of vendor unique bricks, and there was a lot of vendor unique ways of extracting that brick information out of there, and very much vendor unique ways of recovering from that brick, if at all. Starting it in the OCP1 spec is when we had, I'll call it recovery V1. And in this particular case, using the C1 log page, you could describe, okay, if we do have an assert, here's our recommendation in terms of vendor analysis or recovery. There was a lot of cases, I think they believed that these asserts were happening, but there was really potentially no concern of data loss. So there was a method of doing a recovery. That recovery was somewhat prescriptive and said, well, it needs to be a data loss event, but at least you could recover the drive. In OCP version 2 is when we standardized some further debug and monitoring around latency monitor. And we added some improved methods of doing the assert recovery. In 2.5, as we've mentioned several times, this is where we ended up improving the resiliency through having standardized health monitoring and debug. And then the concept is first brought up, and we're going to dive into this more. I'll call this alert and continue recovery was more formalized in the language. And as you can see, Lee already gave a quick hint to this. In OCP version 2. I guess you guys are calling it 6, there's going to be resiliency optimizations, mentioning some comments around cleaning up some of the language around how potentially the alert and continue might work as well as error injection, which would be part of the prevention detection side of this thing. Next slide. All right, so let's deep dive into this for a brief second here. So a lot of this is buried in the language of EREC2, and let's kind of walk through this thing. And the first one here is it says the device should reset itself similar to a firmware update. No host reset action is required, and it utilizes the POS processing status bit to do this recovery. So if a device sees that it's in an unhealthy situation, it takes whatever recovery action it needs to do, but it's not the same as a brick that forces the C1 error recovery or a format command or something like this. This would allow the device to recognize the situation, log it, get the telemetry input into the system, and then raise your hand. And this is by bit number 2 here says the device shall log these events in the telemetry log. So if we do run into one of these events, let's try to recover these things as low impact as we can to the host. But at minimum, we still need to keep the breadcrumbs sitting around to see what happens, so that can be analyzed both by the host and the vendor. And then it includes through reason identifier specifications that they added in here. So we need a vendor specific panic code in the reason identifier. And so with that information, not only do you get the check engine light, but you get that first scoping out of what's going on. And then finally, it does discuss in this thing here, which is let's just get this concept of alert and continue in place with no reset action as an option. So this is all buried mostly in EREC2, but the language is important and leads to some fairly meaningful changes that you might have to an implementation around this. Next slide. So quick summary, there's two supported flows. First of all, it does say in EREC1 or function 1 here, the device shall make every attempt to transparently recover from errors and panics without invoking any of the error flows. There are two of them that exist. There's the one that's the C1 supported airflow, and then there's the log identifier, not using the log identifier C1 workflow support. So walking through, OCP 2.5 documented this flow in greater detail than I've summarized it here. But ultimately what you do is on the system booting up, the device describes what kind of information it needs if it does run into a panic situation, and it raises its hand saying, I've had a panic. How long a pause do I need? What kind of reset actions do you expect? Whatever. Device is in normal operation. At the point that a panic occurs, it's in either an AEN, which I believe is the more desirable method of communicating this. If there isn't an AEN, or the host doesn't, or the drive doesn't have the ability because of the kind of failure it had to issue the AEN, the request is to get the controller failure status bit set. So the operating system would then see a command timeout. It would check CFS and then recognize it's in a failed state. So the C1 log page allows you to describe a delay. So at this point in time, and this is mostly to be able to get the telemetry data properly constructed anywhere between the DA1, DA2 data, possibly DA3, DA4 data, get all that information captured as best as we can. It may take some time, and then the request is to go to the reset. In the specification, has been there for a while there, it says there's a hierarchy of resets that are available. And you should try the least aggressive reset first, followed by progressively higher resets. And the device specifies what reset it can support, and then the host picks from that list. Once you've done the reset, the device is in still a debilitated state, but it's at least in a good enough state that it should be able to capture telemetry. So at this point in time, the host captures all the telemetry that it can get its hands on, hopefully the complete DA1 through DA4 cases. And then will, as described in the C1, it will issue the recovery, be it a format or a sanitize, or potentially a vendor unique command, or possibly you could describe that, hey, all I needed for the recovery was just the reset command, or potentially nothing. And then, you know, the operating system has an option to either stop or it can continue operation. So this requires a fair amount of host integration in this support here to get this capability, and this could be potentially quite an automated process in here. If this is not supported, then ultimately what happens is this is be for the non-C1 flow implementations. Effectively, what will happen is you'll run your IO operations until something bad has happened, like a panic, in which case you'll time out. The CFS bit will be thrown, the operating system will recognize it at that point in time. Likely at all point in time, this stops, and potentially it might be even with human interaction here. The goal is to capture the device telemetry. It's prescriptive in saying you need to issue a format command, and then optionally a reset or a power cycle after the format command may be required based on the vendor. And then you can resume normal operation again. Either flow is supportable. Both flows are described in the OCP spec, and it's really up to the conversation with your customer, between the vendor and the customer, about what the right implementation and the right flow needs to be for your system. I think our advocacy at Micron is just support both, and then if more and more host providers start offering C1 support, it'll be available to everybody. Next slide. All right, so quick summary in all this. Alert through the reason identifier. This is the best way to go do this. So this is between the smart critical warning bits potentially and the alert through reason identifier. We should be able to stop asserting on many cases where the firmware goes, something is notably not what I thought it would be, but I don't believe there's data risk right now. Turn on the check engine light. And reason identifier is a good way to do that. It's in the header. So as every time you read the data area 1, you'll also get the header. You can look for a reason identifier in there. EREC 2 gives the guidance on the panic recovery, and the answer is do it as low of impact to the host as possible, up to the point of potentially taking this very similar to a firmware update, where it's a recovery in place and resume, and then there's just a notification. And then the recovery AN with no recovery resets or actions is a possibility here. So this is one of the things I'd like to work with the OCP authors in the next version of the spec here, which is if we do have this concept of alert and continue, we want to make sure that we understand exactly how best to, if we have a notable but recoverable situation, does it make sense to throw the C1 AEN and throw the bit that says vendor action or vendor analysis required? Or do we just let the region identifier use that as the right trigger? It's good for some further optimization. And then finally, there's the OCP standardized telemetry, which we spent, Mike and I spent time talking about in the fall conferences last year, as well as we talked about in this conference last year. Next slide. Call to actions in all of this. SSD vendors, shift left, enhance resiliency. Implement a panic, an alert versus a panic scheme. Panic where you must, alert where you can. And then be sure to have the implementation for the vendor unique standardized telemetry. It shifts left for a couple of reasons. It gives you an opportunity to potentially ward off problems before it would lead to a panic or a scenario. And second is it'll be a very efficient debug method because everybody has the same OCP CLI telemetry decoder to get to the data. And so it'll give a more unified way of doing an efficient debug for the host vendors. For the SSD host of the Linux Foundation, just implement the host elements to support resilient systems as necessary. Recognize there's a lot of capability to have a high resiliency handshake between the device and the host based on OCP specification. And then for the OCP author contributors is continue to embrace the alert and continue model and add clarity and guidance. It's I think you guys have definitely defined the North Star, but there could be potentially some fairly deep questions remaining on how to get this implemented, and we can get that clarified in the next round or two of specs. All right, that is all I had.
Are there questions for Steve? Mike Lee, I'm not sure which one you're reading questions.
So from Kimoto, the issue logged, is it expected to be persistent through power cycles? And
correct me if I'm wrong, I don't believe it's explicit in the spec that it is. I think our reading on that is yeah, the expectation is these are persistent logs. So the answer is it's very possible there may be a powering down of a platform before it's sequestered into a debug environment, in which case you power it back up and want to pull the telemetry. So I would make the assumption that it's power persistent.
There's there is a requirement to basically don't lose debug information.
Don't lose debug. You're right. You're right. It is in there. Thank you.
And then again from Kimoto, the question is context on resiliency. So yes, the idea is that if you have an issue, you've recovered from it in resiliency, then we still want to know that information and get it pulled. Right. And then Kimoto again, if the issue is related to the link, then power cycle may be necessary. Yes. And so we would hope that if the link is jammed, that you can still do things around force a retrain or things like that. But yes, at some point, hardware glitching or single upset events or weird things, if that we just can't recover from seamlessly, then yes, we have to kind of use bigger hammer, unfortunately.
Okay, great. We're now going to go to lock. Jeff and Eric, you are on next.
Okay. Hi, I'm Jeff Anderson, software engineer at Google. Eric, I think you're on as well.
Yep, I'm here. I'm
Okay.
Eric Eilertson from Microsoft.
Awesome. So next slide. We are collaborating on an effort and joined by others, Samsung, Kioxia, and Solidigm. The following slides will kind of get into the motivation of where lock comes from and the problems it's trying to solve. Next slide. So let's take a high-level look at the life of a data center storage device. It comes into the data center pristine, has no data on it, and then it gets filled with user data. And then it's time for the drive to be decommissioned. Next slide. That drive has a lot of sensitive user data, and we do not want it leaking out of the data center. The drive may be leaving, but the data cannot. Next slide. Next slide.
It jumped to? It jumped like, I don't know why. Give me 1 sec to get back to where you were. I'm sorry. Get back.
There we go. So the most robust way to make sure that the data does not exit the data center is to simply destroy the drive. The problem with that, the problem.
Sorry.
What?
My system just glitched.
Okay.
Okay, hold on 1 second. I'm sorry. Is this the slide you want to be on, Eric?
Yes.
Let's go back to presentation one. I'm sorry.
No worries. Thanks. So shredding a drive is a very good way of making sure that the data on it will not leave. The problem is there are several problems. It produces significant e-waste, and it impacts the bottom line of the drive owner, as they're unable to resell the drive or return it for RMA, the vendor, inhibiting secondhand markets. These drives, in many cases, have useful life ahead of them, but because we can't afford the data on them to leave, in most cases, the drives themselves cannot survive. Next slide. So a technique to address this and to make a drive safe for RMA and resell is to do overwrite. So writing over every piece of the disk multiple times to ensure that any kind of forensic analysis will not yield anything useful for a potential attacker. For this to work, every piece of the drive must be overwritten before the drive is allowed to leave. Next slide. This does not work when parts of the drive fail to be overwritten, such as there's a bad sector. If any part of the drive fails this process, then the entire drive must be shredded. And so we'll still destroy a lot more disks than we would like, even with this technique. Next slide. The problem is further exacerbated with NVMe page management when flash pages may be hidden from the host by the controller. Those pages may have user data on them. And so if we can't even address such pages, we can't overwrite them, and we can't be confident that a drive decommissioned would actually be free of user data. So overall, overwrite is not a compelling strategy for this problem in the long term. Next slide. A more robust solution is to ensure that all data that is on the drive is encrypted with some cryptographic key. And then, next slide, to forget the key. And then as long as you've done that, it doesn't matter that the data might still live on the drive. All that's there is useless ciphertext that cannot be decrypted. Next slide. So this is a thing. NVMe self-encrypting drives manage keys for the user. They allow you to have granularly map different keys, different address ranges. Next slide. And to map those keys to different users with different privileges. Next slide. Now, let's say we've done this and the drive is managing these keys and can be told to erase those keys. That's nice. There is a threat, though, of drive theft. Let's say someone takes the drive out of the data center before we've had a chance to tell the drive to erase anything. If the drive is stolen, the keys inside the drive survive. So yes, the data is encrypted to keys, but the keys are on the drive, and so a determined attacker will be able to recover the keys and therefore recover the data. Next slide. So a mitigation to this attack is to bind that key material inside the drive to a key held outside the drive that would not come with the drive if an attacker were to steal it. There are many different ways to arrange this. You can have the key live on the motherboard or on a remote key management service, but you just want that property that without that key, nothing on the drive can be decrypted. Next slide. In practice, the way this often materializes is through an admin password. You can set up a strong admin password, hold that password off the drive, such as in your TPM, and then rely on the drive internally to transitively protect all the media encryption keys with that admin password, such that unless the admin password is provided on each power on, the media keys are inaccessible. Next slide. Here is an oversimplified diagram of a working implementation of how this could function. An admin password can be provided on power on to decrypt an admin secret, which then is in turn used to decrypt the media keys, which are then used to encrypt and decrypt all the media. So the only thing stored persistently on the drive is the encrypted admin secret and the encrypted media keys, and of course the encrypted media itself. And if you walk away with the drive and not the admin password, then you can't decrypt anything. Next slide. Here is, here we go. Here is an implementation which walks and talks exactly like the prior one from the outside, and yet is fundamentally broken, where instead of using the password to directly encrypt anything, it's simply compared to a password hash to authorize unlock. But the admin secret itself is actually stored persistently within the drive. This defeats the entire purpose of this arrangement, and an attacker who has stolen such a drive could recover the media. Next slide. We can go even worse than this and say, what if the media keys themselves might not even be encrypted properly? And next slide. You could arrange your crypto hierarchy just fine, and yet have an implementation that leaks media keys out of external interfaces or via glitch attacks. Well, that's not good either. Next slide. So the overall problem that faces us is that it is critical to get the storage key management right to make sure we address all these significant threat models. The implementations that we see addressing these vary in quality, and it behooves us then to carefully audit these implementations. SAFE is an effort to amortize that cost, but it still is a significant cost. So I will hand it over to my colleague Eric to discuss how we are approaching this problem.
Yep, so let's go to the next slide. So maybe we've heard several times here today, Calyptra was mentioned. This was mentioned in previous OCP conferences. So this is an open source root of trust for measurement and identity. It's part of OCP with the implementation living under CHIPS Alliance. So this is a way to have an open and transparent where all of industry can put their effort into making one good instance of this hardware block and the IP. And then we can try to leverage that in other places. So the lock program we're talking about now is going to build on Calyptra, taking Calyptra as is and building onto that and trying to add in some more key management, but all this open and transparent so everybody can make use of this. So we can move on to the next slide here. So now, introducing lock. This is a little bit of a backronym. So it's layered open source cryptographic key management. So this is, an effort to deliver an open implementation that everybody can look at. You can have your own security teams look at this to make sure you're confident in the implementation. I know Microsoft and Google are having their own people, as we go through this, looking at this, threat modeling it. what do we need to do to meet our own security bars. And that's, have this to provide the key management services to the drive and to the host, but leveraging some of the services provided in Calyptra. So we can move on to the next slide here. So at a very high level, these are kind of some of the blocks that we're thinking of. On the right, you have your storage controller firmware and AES crypto engine that device vendors have had for years. It's their same firmware where today they manage the keys in there, do their key derivation, their unwrap, pass them to their crypto engine. It's their own implementation. And they optimize for their target markets and their engineering processes. Now we're trying to implement here on the left side here, building on Calyptra, but also adding on this key management block. So this would be the hardware and the key management block. It's the hardware and firmware necessary to do key wrap, unwrap, key derivation, all of the sensitive key handling mechanisms we've done in this key management block. This is to reduce the trust placed on the controller firmware. So we can move on to the next slide. I think we're kind of just going to walk through this a little bit more. So the AES crypto engines, this would still be the current the vendor, their AES crypto engines hooked up to their high-speed data pipeline, coming in through PCI Express or whatever that might be. It's their high-speed data path, and we're not going to change that at all. If we can move on to the next one. So the controller firmware, we envision this to be largely untouched. There will need to be some changes here to, we're guessing half dozen, maybe dozen commands that are going to have to change to call out to the key management block, where they could request, key wrap, key unwrap, insert a key, delete a key, that type of operation. So we can move on to the next one. So, like we'd mentioned a little bit already, so the key management block is what's actually going to generate the secrets and wrap them and store them. So this is the trusted entity. This is the one thing that will see raw encryption keys. Only in hardware. We don't want to have firmware have access to these secrets. We want this to be immutable logic that has access to secrets. And we can move on to the next slide. So then the key management block after the key derivation is going to pass these keys directly to the hardware crypto engine. Still trying to figure out exactly what that looks like. It might be a register interface. That's kind of where we're leaning now, but we'll have to see where that lands. We can go on to the next. And Calyptra, we've talked about this before, but Calyptra is going to provide the attestation services. So the higher level, the cloud provider or, the customer in a cloud provider or a tenant could, ask Calyptra through attestation, get down to Calyptra, hey, which device am I talking to? How are you configured? Am I comfortable releasing my keys here? So that's kind of how Calyptra ties into the attestation there and its identity and how it's configured. And provides the stable identity as well, which is needed for part of our key management. So we can move on here. So, and then in the trust boundary here, so Calyptra and the key management block are going to be trusted. Key management block will have access to your media encryption keys, and then it should be only hardware in the crypto engine. But we've largely removed the need for the controller firmware to be trusted. It still could cause some denial of service and things like that, but it shouldn't actually ever see media keys, so it can't leak the keys. And we think this is going to be necessary so we can actually, have confidence in, destroying the keys and forgetting the keys. If we know that nobody had a chance to leak the key, then we have the confidence necessary to trust crypto erase, and then we can no longer be shredding our drives. So move forward to the next. So I guess I kind of already mentioned this a little bit, but the high-speed crypto engine, we're just passing keys into that. The vendor can still develop and integrate, develop their own high-speed data paths, do innovation there. We don't want to get involved in that. We don't want to slow that down. You should keep innovating in that area. So we can go on a little bit more. So here's a quick overview, very high level of what the key hierarchy might look like. So, the external root seed here, this could be your pin from TCG Opal. That gets passed in along with, to decrypt your storage root key. This is then used to decrypt some of the wrapped device secrets, which again, changed again and allows you to decrypt the media encryption keys. So this could be a different media key per, different tenant or namespace, depending on how you're managing your drive. And then these keys then get passed into the hardware engines for the actual high-speed encryption and decrypting the raw media. So high level. So luckily, the controller firmware never sees raw secrets. It only would see wrapped secrets. So we're, removing the need to trust the controller firmware or reducing the need to trust it. So we can move on to the next. So now, call for action. So, we plan on delivering this, this IP block, whether it's, it's going to be RTL, ROM, and firmware, but, we need help from the community to make sure we're covering all the features and the needs of everybody. And we want to ensure that we have secure key management and, we have high confidence in the ability to do a crypto erase to delete these keys so we know that this happened. We're hoping to get a 0.50 spec later this summer. And we invite you to, you're already members of OCP, but also join CHIPS Alliance if you'd like to collaborate and work on the implementation. And I think with that, we're moving to questions.
Great. Lee, do we have any questions? By the way, I should note, Jeff is the OCP lead for the security project. As you know, we should know that at the beginning. So
I forgot to introduce myself properly.
I'm sure he would love to have you join his project and participate. Lee, do we have questions for Jeff?
Yeah, so one question, and kind of our usual question from Naga. Where can I find the working draft of OCP lock specification?
So it's currently being worked on. We hope to get something out soon. TBD, stay tuned.
Any more questions?
Well, there's one from Pankaj, but it's for Javier, so we'll probably have to answer that one offline because I think Javier had to drop.
Okay. If there aren't any more, then we are going to go to our community update. So thank you, Jeff. Thank you, Eric. I appreciate you guys coming today and sharing all about this. Very interesting.
Thanks for the time.
Okay, Rob, Michael, Steve, you guys are on.
All right, thank you so much. A little less technical and a little more process. You have the three of us from the Open Compute Foundation here. For those of you who are not familiar, I am Rob Coyle. I'm our Community Technical Program Manager. I'll start off our presentation around our contribution process, which is a lot of these specifications and works in progress that you're looking at. I'm going to do a quick update and a review of that, and then I'll hand it off to Michael. Michael will give you an update on the community, and then he'll pass it off to Steve. So for the contribution process updates, we recently updated the contribution area of the website. I'll touch on that really quick. We'll go through the contribution process, and then we've added an errata process that I'll review with you as well. So here is the link in the area of the contribution process page. There is lots of good information here. It's not just a for beginners who have never seen OCP before. If you're active in our community, please come back to these website pages. We're updating them all the time. There's useful links here at the top of the page that'll take you through the overall journey, but then also some critical information, including documentation, agreements, and updated templates. And I see Michael just dropped the link in the chat there, which is super helpful. Thank you. So the contribution process has not really changed. We've just added some clarity around the steps. And if we included the different ways you can contribute to OCP, And some of these types of contributions have a little bit different process. For example, our specifications require a contribution license agreement and a final spec agreement. They also require that you present to both the project and our steering committee. In contrast, white papers don't have as many critical steps. Though you can use a contribution license agreement in a white paper, more commonly we see things like Creative Commons referenced in those documents. And then our white papers as a non-specification don't require a presentation to the steering committee. And then each of these different variations have different steps. So if you go to this area of the website, there are contribution steps based on each type of contribution. So please take a look there at the website. Within that area, the contribution agreements page has also been updated. If you've seen it in the past, it was a very long bulleted list of just every agreement you could potentially use. We've done our best to try and organize this based on the contribution type. So here in this example, we have hardware specifications, the different templates that would be used for an all-in-one specification, a base specification, design, and product specification. Those are all different. And then the associated licenses are in the next column over to the right that are associated with that contribution. Our errata process. So there were questions and work around needing to submit a complete new document. And then depending on the level of update to that document, if it was already past the review process, it had already been published, we were requiring, our process required our contributors to go basically through most of the process all over again, and it wasn't very efficient. So we've added an errata process, which I won't read bullet by bullet here, but essentially if you have minor updates, references have changed, or there were omissions or number changes that really didn't change the content of the document in a material way, it was really just a correction. An errata, which the template exists in that agreements page and in the how to contribute area, you can grab that template. It's essentially a cover page that lists what are the changes, a description of the change, when it was made, and then it can be added essentially to the top of the document. So I'm happy to help in that process. If you have a contribution that's already been published, you've noticed something, oh, we forgot this, we need to add this, that's actually not the right link or page number, I can work with you to make sure that this form gets added to the top of that contribution. And it's just an efficient way to make small corrections. And I think that's it from the contribution process. Please reach out to me if you're thinking about contributing something, something doesn't make sense on the website. We really want to have good visibility on anything that's coming. As we get closer and closer to Global Summit, the schedule for steering committee and project meetings gets very, very busy. So we are entering the rush period. So if you think you want to get something published before Global Summit, or you want to announce it at Global Summit, please let me know and make sure we get you on the schedule. Over to Michael.
All right, thanks, Rob. Hey everyone, my name is Michael Schill. I'm the Director of Community for OCP. Got just a few updates that we want to share with everyone. We appreciate you attending. Go to the next slide there, Ross. Thank you. So first, want to let everyone know that earlier this year, we published a new operating structure and policies document. This replaces the former governance document of OCP. Covers a lot of the day-to-day details and how our projects are governed, gives you some insights into the inner workings of the foundation, and explains, a bit more about the overall strategy of the OCP Foundation. I encourage you to take a look at that document. Feel free to read through it. Reach out to me if you have any questions. Happy to sit down, have a call with you, and go over those. Just a few key highlights that were made in the most recent update. We made some updates to our volunteer leadership requirements. In previous iterations, we've had a limitation on the number of folks who could serve as co-leads. We've now removed that limitation, and now we're strictly stressing that we want to have enough redundancy in a project to make sure that we cover all angles, from technical expertise, subject matter expertise, but also administrative and project management skills. So if you are interested in helping lead an OCP project, but maybe you felt that you were lacking in one area or the other, we have ways to get around that now, and encourage you to reach out to me, and we'll see how we can get you best plugged in. Next point here, Rob was kind enough to go over our contribution process, the different ways that we've streamlined that, particularly when it comes to white paper and case study contributions, which Rob has already outlined. There's some new programs at OCP that we're really excited about. You may have heard them announced at the OCP Global Summit last October, and then again at the Regional Summit in Lisbon just a couple weeks ago. I won't go into detail on SAFE or the Experience Center program. I believe Steve will cover those right after me. Next slide, Ross. Again, I'll go over this quickly. This falls in line with some of the changes that we're planning on making to the contribution process, or have made rather. We're seeking to streamline the OCP contribution process under one set of CLA and FSA, which stands for Final Specification Agreements. Again, I won't go into detail here, but encourage you to reach out if you have any questions. Happy to sit down and explain the reasoning behind some of these changes. Overall, hoping to make the process, again, just easier for our contributors. In a similar manner, we're in the process of adding a feedback agreement for contributors. This is something that the storage project has been asking for some time, and we're happy to announce that we are right on the cusp of being able to get this ratified and get this agreement in play. The crux of the agreement here is that it will allow folks who would not otherwise be part of a contribution to give very specialized, very technical feedback in a safe and yet open manner. So more to come on that feedback agreement once that is published. We'll be sending out an alert to the entire community, but did want to give this group a heads up, as it was the storage project that set this in motion. I think over a year ago. Mike Allison will chime in and correct me if I don't have that date quite right. It might be closer to 2. Next slide, Ross. Recap of the regional summit. We did not have a storage track at the regional summit this year. Instead, we have this wonderful storage workshop, which I'm happy to see so many familiar faces on. But I know that some of you attended the regional summit. Just a quick recap: if you weren't able to attend, but you're interested in the content there, or maybe you attended and saw a talk that you particularly want to share again, you can find nearly all the slides and recordings on this link here under our past events portion of the OCP website. There are a few talks, I think it's less than 10, that are not yet up. That's because some of our production equipment is actually held up in customs. So as soon as we get that equipment through, we'll be able to get 100% of the recordings up. I think we're somewhere between 90 and 95% right now. Some other quick highlights. This is the most highly attended regional summit we've ever had. Some nice growth from last year in 2023, and looking forward to continuing that on in 2025, where we'll be in Dublin, Ireland. So going from sunny Lisbon to cold, wet Ireland in April, but I do hear that Ireland has good beer. So maybe we can make it for the weather that way. Hope to see you guys there next year. Next slide, Ross. And then the last point that I'd like to chat about here before I turn it over to Steve, who's gonna go into stuff that's a lot more interesting. Here is our Global Summit update. So as you all know, the Global Summit's coming up in October. Registration starts in June. Speakers do get a free pass, as you all know, so encourage you to submit. And my last bullet point here is actually incorrect. The call for presentations has actually already launched. It launched on Monday, and the deadline for the abstracts is June 21st. So you still have about 5 weeks to get abstracts in. And just a reminder, we only need a few sentences in order to get your abstract in and get a placeholder to speak at the summit. So encourage you all to submit for a talk. With that, I think I can hand things over to Steve Helvey. Steve is OCP's Vice President of Emerging Markets, here to talk to us about the OCP Marketplace and a few of the other programs that you've heard mentioned today.
Thanks, Michael. Eric and Jeff from the security group are quite involved in this. I will cover this at a high level. The SAFE program was launched in October, and it is really spearheaded by Microsoft and Google, providing a systematic security appraisal framework for firmware. And the security group has taken this initiative and led with their efforts. I see more device vendors and more things happening around storage than any other group around SAFE so far. So next slide, Ross. The business problem that they were set out to solve is that their security reviews that are being provided by third-party auditors are happening at one point in time only. They're happening late in the production cycle, and many of the customers are asking for the same type of audit on the same type of device without really adding any value, but just adding a lot of redundancy and a lot of cost. Next, Ross. A few of the key components to the hardware integrity that they're solving for is a security assessment report, providing the assurance that the firmware is trustworthy, a software bill of material, the integrity manifest, and of course, the root of trust piece. All of these things were really core areas and core components that they thought through with the OCP SAFE program. Next, Ross. So this slide builds out, Ross. First of all, if you're interested in the SAFE model, here's how it works. So the SAFE project team or the security project team has put together a set of requirements and a set of review areas. So the requirements are with the third-party auditors that are approved by OCP and the security committee to be a third-party auditor for SAFE audits. Within also this criteria, there are areas of review that the audit will take place on that particular device. So that's community driven, and that is available on the OCP SAFE GitHub. Next, Ross. So from that, a device vendor will contact an approved OCP SRP, engage in an audit. The SRP and the device vendor will mutually work through that audit and then mutually decide when that short form audit report is viable to be published on the OCP GitHub. So that is happening behind the scenes. OCP is not a security body. That all happens between the SRP and the device vendor. We are simply the governing body and the framework that allows these audit forms to be published in the open. And then from that, the device vendor can have their solutions badged as OCP SAFE and listed on the OCP marketplace. And we hope that this reduces the redundancies in the audits. And we hope to have this as a downstream impact on companies in the market that may not have the resources to go have an audit done. This is to up-level the posture and the conversation around security and to know that these companies are moving forward on providing this a framework. Next. Here are the details. We have one device currently with more in the pipeline. It's the SK drive that came through in October. If you go to the OCP marketplace under products, you can search and filter for OCP SAFE, and you can see the product itself, and you can also link to the short form report that was done by one of the SRPs or the IO active on this particular case. Next. More details. These are all links that will be sent out later. If you have any questions, feel free to contact me. Happy to walk you through it. Next. Let's get to the OCP marketplace. These are just a few highlights from Q1, and the storage area has grown considerably over the last 18 months here. So next. This is the storage ecosystem on the OCP marketplace. On the left-hand side, you see upper left quadrant, you see several of the device vendors. On the right, you see testing services that we are now offering around OCP devices, Teledyne and UNH. WeWin is providing storage systems. The rest of these logos, IOActive, Tetrol, NCC, Rescure, Atreides, and Trailabits, are the security review providers that are approved to be OCP SAFE providers. Next. All right. Listings, so far we're over 275 on the marketplace overall. Over 60 OCP members are now part of the program, and we're continually seeing above 10,000 views per month. In Q1, we were up over 13,000, which is nice. The majority of those folks are looking at the product section within the OCP marketplace, and on the right, you will see the breakdown of the top 10 or so countries, and that list does not change that often. Maybe one or two in the bottom drop in and out, but the top 5 or 6 are always in that order. Next. This is one of the more pleasant things to note around the OCP marketplace are the number of drives that have come onto the marketplace in the last year. You will see 8 drives here, and I want to call your attention to the bottom right where you see a Samsung drive that is the first drive that has been OCP inspired, approved, and recognized for the 2.5 specification. So we're really excited about the momentum and the passion that these providers have had around getting on the marketplace and promoting their solutions. Next. As I mentioned, we do have testing services. This is under storage, as well as you'll find it under another section of our marketplace, highlighting what Teledyne is doing for storage on OCP and what the UNH is also offering. Next. Under a particular area of the OCP marketplace, under facilities and services, you will see OCP experience centers. These can take various forms. They can be a simple demo lab. They can be an executive briefing center. They can be a test and validation lab or a briefing center, or really we leave it up to the member to decide, but they do have to be a member of the solution provider program. They do have to be active within the marketplace area. We have 3 of those focused on storage. We have the 2 that I mentioned around UNH and Teledyne, and we have the great Samsung Experience Center set up in Korea, which is really quite impressive in their executive briefing center focused on OCP SSDs. Next. The WeWin storage systems. These are the 3 storage systems that we have currently listed and always open to more, but these traditionally get some decent views. I'd like to see a bit more coming through here, but the drives themselves, back to the SSDs, 2 of those drives are continually in the top 10 most viewed products of the entire marketplace. The Samsung drive and then the SK Hynix drive has been in the top 10 now for a couple quarters. So the drives continue to show strong momentum. The systems are a bit further down the list. Next. That's it. Take a look at the marketplace. If you have any questions or your device manufacturer or questions about the safe, let me know. Happy to help. That's it. Thanks, Ross.
Great. Lee, do we have any questions while I go to the next session we're going to go to?
No new questions.
No new questions. Okay. Let me move our slide deck along. We are to the last. This is the end. You made it to the end. Congratulations. So with that, a few things in closing. Contributions, we're doing great. Marketplace, you saw, we got a significant number of new SSDs, test providers, collaboration on meaningful topics, very much results in meaningful products. I want to thank all our speakers here. We had a lot of great speakers. I want to thank you for all your hard work. So very much thank you for coming. You are the guys who made this successful today. I want to thank all our sponsors. All our sponsors today, really appreciate FADU, Micron, Samsung, SandBlaze, ScaleFlux, SiliconMotion, Teledyne, LaCroix. Thank you, all of you, for sponsoring us today. And with that, our call to action. There are opportunities. Present your ideas in the monthly meeting. Reach out to me and Lee, and we can set that up. Contribute to OCP. We see the value of the contributions here today. Participate in Marketplace is a great opportunity. And, I think what we've seen is the overall theme today is collaboration on real-world problems leads to great ideas, resulting in great products. And so with that, thank you very much. And I appreciate you attending today. Thank you.
Thanks, everybody.
Thanks, everyone. Thank you, Ross, Lee, Mike, for putting this together.
Yeah, fantastic job, guys.
Thanks.
Great
Great
job,
job, guys. Thank you for hosting this for us.
Thanks, Ross, and all.
Everyone, just as another quick reminder, recording and slides of this talk will be up on the OCP website under past events within the next day or so. So feel free to take a look at that. We'll also post it on the OCP YouTube channel for everyone to see.
Great, thank you.